Now let's begin our discussion for bases. Bases are compounds containing OH and they turn red litmus to blue. So now let's move on to physical properties. Taste. They are generally bitter in taste. They are soapy to touch. And they have mild corrosive action on skin. They turn red litmus to blue, and as I've already discussed, they ionize completely in water. Most of them ionize completely in water. Now they have different, for example, they turn red litmus to blue, so blue litmus won't have any action. They turn phenolphthalein to pink. They turn moist turmeric paper into deep brown. So that was discussion regarding the color developed on different indicators. Now let's move on to chemical properties. So with metals, they liberate hydrogen gas. Zinc reacts with sodium hydroxide forming sodium zincate, releasing hydrogen gas. With aluminium, it forms sodium meta-aluminate, that is NaAlO2, and liberates hydrogen gas. So you could put 2 moles of O2. Okay. Now with non-metal oxides like carbon dioxide, it forms sodium carbonate, Na2CO3, and water. With acids, it undergoes a simple acid-base reaction, which is neutralization. You have acid reacting with base, so it forms a water molecule. So you have KCl plus H2O. Similarly, NaOH can react with H2SO4 to form Na2SO4, releasing water molecule. Simple reaction of acid with a base to form salt and water. Now with salts, so let's take an example of ammonium chloride. Sodium hydroxide reacts with ammonium chloride. So in this reaction, ammonium ions combine with OH to form ammonium hydroxide, and then a salt is formed. So one base reacts with another salt to form another base and another salt. You have reaction with other salts. So let's take an example of iron chloride and zinc sulfate. Sodium hydroxide reacts with iron chloride to form sodium hydroxide react with iron chloride to form iron hydroxide, or you could write it as iron 3 hydroxide, and it forms a salt which is NaCl. So you could balance it by putting 3 moles of sodium hydroxide. Similarly, sodium hydroxide reacts with zinc sulfate. So in this case, you have zinc hydroxide getting formed. You have ZnOH twice. Sodium hydroxide reacts with zinc sulfate to form zinc hydroxide and sodium sulfate, which is Na2SO4. That means one base reacting with other salt to form another base and another salt. So this was basically the reactions and physical and chemical properties of bases. So we started with physical properties. It tastes bitter, it is soapy to touch, has mild corrosive action, and it turns red litmus to blue. It ionizes completely in water, mostly all the bases, and then except ammonium hydroxide, which is a weak base, and then it turns phenolphthalein, which is an organic dye, to pink. It turns moist turmeric paper to deep brown. Then we started with chemical properties. With metals, it releases or liberates hydrogen gas. So with zinc and aluminium, it forms sodium zincate and sodium meta-aluminate, releasing hydrogen gas. With non-metal oxides like carbon dioxide, it forms sodium carbonate and releasing water molecule. With acid, it undergoes simple neutralization reaction to form salt and water. And then with salts like ammonium chloride, it forms corresponding ammonium hydroxide releasing sodium chloride. With other salts, it forms a different type of salt releasing a different type of base. You have sodium hydroxide reacting with iron chloride to form iron hydroxide and sodium chloride. Similarly, sodium hydroxide reacts with zinc sulfate to form zinc hydroxide, which is again a base, and it releases sodium sulfate, which is a white colored powder. So this was about the physical and chemical properties of bases. Now let's study the role of acids and bases in water. So acids, let's take an example of dry hydrogen chloride gas. So dry hydrogen chloride gas doesn't ionize, but when you have hydrochloric acid, when it is dissolved in water, you have HCl ionizing into H plus and Cl minus. Now this ionization takes place in presence of water. Such reactions are called as dissociation reactions. So I would say that anhydrous acids like anhydrous hydrogen chloride or HCl gas doesn't ionize. They do not behave like acids if ionization is the only aspect through which acids can be distinguished. So HCl dissociates, giving H plus plus Cl minus. If I could write this using hydronium ion, in terms of hydronium ion, you have HCl plus H2O, that is water. It forms H3O plus, which is hydronium ion, plus Cl minus. Now you have a cation and you have an anion. So they are going to conduct. That means acids, when they are acids or bases, when they are dissolved in water, form a conducting solution. Similarly, when you have sodium hydroxide, when this is dissolved in water, it produces Na plus plus OH minus. So in this case, again cation and anion is produced, so it forms a conducting solution. So all acids or bases, they form a conducting solution only when they are dissolved in water. They do not ionize. They do not ionize when they are in their anhydrous state. In their anhydrous state. Now let's try and understand what exactly is the role of water in ionization. Is it possible that if you have any other non-aqueous solution and still ionization can be possible? Now let's study what exactly water does. Now let's start with hydrogen chloride or HCl. When you dissolve this in water, you have HCl dissociating, giving H plus and Cl minus. Now ideally a positive and a negative charge attract each other. So H plus should combine with Cl to form HCl and the reaction should be coming back. So this should be ideally a reversible reaction, but this is not a reversible reaction. Now let's try and understand how exactly a water molecule looks like. We can write water molecule as HOH. Oxygen is more electronegative than hydrogen, as a result of which it pulls the electron pair towards itself and it gets partial negative charge, and these two hydrogen gets partial positive charge. So it behaves like a dipole. So when you have hydrogen chloride, when it is dissolved in water, these water molecules form an envelope around the H plus and Cl minus ions. So let's try drawing the envelope. You have H plus ions. Now let's try to orient the water molecule. You have oxygen with partially negative charge. So this oxygen with partial negative charge, and you have hydrogen with partial positive charge over here. Then this, let's try to draw another water molecule. You have OH, H. Then let's try to draw one more water molecule. You have OH, H. Again, let's try to draw one more water molecule. Let's try drawing one more water molecule over here. So now these dipoles start getting attracted towards each other. So I would put partial negative over here, partial positive partial positive, then you have partial positive here, partial positive here, partial negative, and this is getting attracted to hydrogen, and then again you have partial negative, you have partial positive, you have partial positive over here, you have partial negative over here, and you have partial positive over here. So now this hydrogen atom is completely trapped, and this is not allowed to recombine with Cl minus, as a result of which the ionization of HCl goes to completion. Now let's talk about Cl minus. Is Cl minus also existing in this manner, or it is free? So you have Cl minus, which is a negatively charged ion. So this is enveloped by the water molecule in different orientation. So now in this case you have H, and then you have oxygen. Similarly you have one hydrogen over here, one hydrogen connected to oxygen. Similarly you have hydrogen, this is connected to oxygen, and then again you have oxygen and then two hydrogens. So now let's try putting the polarities. So this is partially negative, this is partially positive, this is partially positive. Again this is partially positive, this is partially positive, this is partially negative. This is partially positive, you have this as partially positive again, this is partial negative. Again you have this as partially positive and partially negative. So now this Cl minus is again enveloped, as a result of which it is not allowed to combine with H plus. This is the reason HCl conducts only when it is dissolved in water. So this is the basic reason why you have all acids, they do not show any conductivity in their anhydrous state. So this was about the role of water in ionization. The corresponding corresponding atoms, they form envelope around their H plus and Cl minus ion, as a result of which the ionization of HCl goes to completion. And the reverse reaction, that is H plus combining with Cl minus to form HCl, does not happen. So now acids and bases, they have their own definition. Some say that acids are the compounds containing hydrogen ions. There are certain acids which don't contain hydrogen atoms. So now different theories were put forward to explain acids and bases. So the first and the foremost theory was put forward by Arrhenius. According to Arrhenius' theory, acids are hydrogen containing compounds and they ionize, giving H plus ions in the solution. So if I have to write down the ionization of HCl, I will write HCl aqueous, that is dissolved in water, produces H plus and Cl minus ions. If I have to write sulfuric acid, which is H2SO4, I would write H2SO4 aqueous, that means dissolved in water. It produces 2H plus SO4 2 minus. Then if I have to write nitric acid, which is HNO3, I would write this as H plus NO3 minus. So acids are those species that contain only hydrogen ions. They ionize, giving hydrogen ions in the solution. So this was basically the definition for an acid or a base in the case of Arrhenius theory. Similarly to acid, you have base. Bases, they contain OH minus ions. So bases like, let's say, calcium hydroxide. Calcium hydroxide ionizes, giving Ca2 plus, that is calcium ions, and hydroxyl ions. So similarly bases are hydroxyl ion containing compounds which ionize, giving hydroxyl ions in their aqueous solution. So this was the basic definition of an acid or a base according to Arrhenius. But as the technology advanced, as different researches came into play, they realized that Arrhenius theory has its own limitation. You take an acid, you dissolve in water, you get H plus, and OH, in the case of base you get OH minus ions. Is it really the definition of an acid? Is the definition of an acid or a base restricted only on these aspects? The answer was no. We have certain compounds, they can be dissolved in non-aqueous solution, like for example liquid ammonia. So Arrhenius theory had one important limitation: it was applicable only to aqueous system. Applicable only to aqueous system. So it didn't give any idea for the definition of acid or a base, whether it would remain the same or whether it would change when the corresponding acid or a base is dissolved in a non-aqueous system or non-aqueous solution. Now have a look at these oxides: sulfur dioxide, phosphorus pentoxide, carbon dioxide and nitrogen dioxide. They don't contain hydrogen ions, or they don't contain hydrogen in their molecule, but still their aqueous solution behaves like an acid. You have SO2 dissolved in water forms H2SO3 sulfurous acid and sulfuric acid, which is H2SO4. Similarly, P2O5, it forms phosphorus acid and phosphoric acid. Carbon dioxide forms a weak carbonic acid. NO2, it forms HNO2, HNO3. These compounds don't contain hydrogen, but still their aqueous solutions are acidic. Arrhenius had no explanation regarding these aspects. Now we move on to another compound, which is aluminium trichloride. It exhibits acid behavior. It does not contain H+ at all. It is just a metal bonded to a non-metal. So it has certain characteristic features because of which it exhibits acidic nature. Again, Arrhenius had no explanation regarding this aspect, because of which his theory was discarded after a period of time. Now let's move on to Arrhenius theory. A quick recap. According to Arrhenius theory, acid is any hydrogen containing compound that can give H+ ions in its aqueous solution, and the most important aspect is H+ ions do not exist independently. They always react with water molecule and exist in the form of hydronium ion, which is H3O+. So all acids ionize giving hydronium ion. This could be one of the definition. Similarly, bases ionize giving hydroxyl ion in their aqueous solution. Then we moved on to the limitations. Arrhenius theory was not applicable to non-aqueous solution. He had no answer why certain compounds behave like an acid in non-aqueous solutions, and it was applicable only to solutions in water, that is aqueous solution. Certain oxides like sulfur dioxide, phosphorus pentoxide, carbon dioxide, nitrogen dioxide, they still don't contain hydrogen atom, but their aqueous solutions are acidic. Arrhenius had no explanation regarding this, and Arrhenius was not able to explain the acidic nature of aluminium chloride, which is AlCl3. These facts led to the failure of Arrhenius theory, but still some aspects of his theory were greatly appreciated, and still we have the first definition of acid and base coming as compounds having H and OH, which is still accepted even today. Now let's begin our discussion with the next theory, which is Lowry-Bronsted theory. According to Lowry-Bronsted theory, an acid is a proton donor and a base is a proton acceptor. Now an acid, since it is a proton donor, so HCl, it gives H+ and Cl-. Now as we all know that hydrogen has 1 electron. So when it forms H+, that means it has 0 electrons and it has 1 proton. So that is the reason we call this H+ as a proton. So acids are proton donors and bases are proton acceptor. Now let's take a very simple case of HCl undergoing ionization. When HCl is dissolved in water, you have HCl as an acid and H2O is base in this case. So HCl donates a proton to H2O, as a result of which it forms H3O plus Cl minus. So water can exhibit a dual behavior, that is behavior as an acid when it reacts with a base and behavior as a base when it reacts with an acid. Now in this case you have an acid, it donates a proton to base which is water and it forms H plus or hydronium ion and Cl minus. So in this case you have water behaving as an acid because according to the definition of Lowry-Bronsted base, base is a proton acceptor. So H2O accepts proton. So this is a base. Similarly, you have HCl, it gives proton or it donates a proton. So it is called as an acid. So the advantage of this theory was that he was able to explain a very important phenomenon known as existence of conjugate acid-base pair. So if you could see this, you have HCl and you have Cl minus. So HCl and Cl minus differ by a single proton. Similarly, H2O and H3O plus also differ by single proton. So Lowry-Bronsted gave them a term known as conjugate acid-base pair. So you have HCl, which is an acid, it donates a proton and becomes Cl minus. So this is called as acid and this is called as its conjugate base. And similarly, H2O, which is a base, it accepts a proton and it forms conjugate acid. So he defined conjugate acid-base pair as an acid-base pair. Now members of which can be formed from one another by transfer of a single proton. For example, if I have HCl, I can have, this is an acid, so I can form its conjugate base by removing a proton. So I get a conjugate base. Similarly, if I have a base which is H2O, this can accept a proton and form a conjugate acid which is H3O plus. So conjugate acid-base pair are the acid-base pairs members of which can be formed from one another by transfer of a single proton. Now let's consider this reaction. You have acetic acid ionization. So acetic acid ionizes in water and the ionization is reversible. It forms CH3COO minus plus H3O plus. Now in this case you have acetic acid which is the acid and you have acetate ions which is the conjugate base. So this acid is called as acid 1. We write normally conjugate acid base pair as acid 1 base 1 and then acid 2 base 2. So you have acid 1 and this conjugate base is denoted as base 1. Similarly, you have the next pair. Here in this case you have a base which is H2O. It accepts a proton and it forms a conjugate acid. So if this is acid 1 and this is base 1, this has to be base 2 and then you label the conjugate acid as acid 2. So it can be clearly understood that acid 1 base 1 is one conjugate acid base pair. Again acid 2 base 2 is another conjugate acid base pair. Another important fundamental is if you have an acid which is strong, then its conjugate base has to be weak. And if you have a base is strong, then you have its conjugate acid which it will be weak. So it is completely a contrasting pair. A strong acid will have a weak conjugate base and a weak acid will have a strong conjugate base.